Hello everyone. In this lecture we will study vapor absorption refrigeration system. Okay. First of all, in last lecture we studied vapor compression refrigeration system, and the cycle is represented by this. Okay. So process 1 to 2 is compressor, 2 to 3 is condenser, 3 to 4 is expansion, and 4 to 1 is evaporator. Okay. But what happens, like if we say that work input, if we talk about work input to the compressor in the case of VCRS cycle, we know that work input for open system is given by VTP. Okay. Now the pressure is constant from V1 to V2. Okay. Sorry, P1 to P2. We have constant pressure difference. Okay. So what is the deciding factor for our work input? So our V, specific volume value, is the deciding factor. Okay. Now in generally in condition of compressor, we use the our inlet is in gaseous form, vapor form, so we use the value of Vg. Okay. So since this value is very large, so work input to the compressor is very high. Okay. Now to decrease the work input to our compressor, and so what we do, we try to reduce this specific volume. Okay. So first thing, we can do, we can decrease it to wet region. Okay. In wet region, specific volume is value is less. But what happens in wet region, our compressor, it is harmful to compressor, harmful to compressor. Okay. Now let's say that, so to overcome this difficulty, if we say, let's consider V to be Vf, we know that Vf value is very less than Vg. So it means that if we can convert the fluid, compress the vapor, liquid into directly to the high pressure. Okay. So what will happen, our one input will be very less. Okay. Will be very less. Okay. Now to overcome this difficulty, we have came across to vapor absorption refrigeration system. In this, what we do, we increase the pressure of fluid, liquid, to the higher pressure. Okay. Now if we want to draw the system for VARS, that is vapor absorption refrigeration system. Okay. So this was earlier I have drawn for VCRS. Now in VARS, what happens that this compressor is removed, and some new components are applied in the system, which result in our vapor absorption refrigeration system. Okay. Now let me draw what are the new components that are installed. Okay. So first one is generator. Then what we do, then another part is absorber. And there is a throttling in here. This pressure reducing valve is used here. Okay. From generator to absorber, and a pump is installed to increase the pressure. Now here we have installed a pump. So this is our okay, and we use this pump to increase the pressure of the refrigerant in absorber to generator pressure. Okay. This is our pump. Okay. So so here is this state 1, exit of evaporator. Okay. And at state 1 it is entering the absorber, and state okay. So we will discuss these states later. Okay. We will redefine it later. Okay. Now we can directly remove the states. I will just show the direction of the flow. Okay. So what happens in case of VRS, this system here, this system here is our replacement of compressor in VCRS of VCRS, sorry, of compressor, replacement of compressor of VCRS. Okay, so what we have done here, with the help of generator, absorber, our throttling device and pump, we have what we have done, we have replaced the compressor. Okay, now here only work one device, work input device, that is our pump, and this work input is very less than that of not very less than that of compressor. This value is very low. Okay, I hope you understood here. Okay, now here this generator is our heat absorbing device. Let's say that it is taking some heat, absorbing, releasing some heat. Okay, and from here we can see that our work input very small, and major amount of input energy is in form of heat, Q input. Okay, we have to provide the major amount of an input in the generator. Okay, now I will moving forward. Let's talk about principle of absorption system. On what principle does absorption system work? So number one point is, some substances have affinity for another substance at some temperature, at some temperature at some temperatures and pressure conditions, and less affinity at another condition. Another condition. Okay, now we have some examples here. So first example is ammonia, sorry, ammonia plus water. Second example, let's talk about water plus lithium bromide. Okay, now this ammonia in ammonia water is our refrigerant, and this water act as absorber. Okay, this water here act as refrigerant, and this lithium bromide is our absorber, and this lithium bromide is in solid state. Okay, okay, and there are many more examples like ammonia, lithium nitrate, and ammonia calcium chloride, or water lithium chloride. Okay, but we will stick to these two only. Okay, now let me draw this VRS system in an in enlarged manner. Okay, so here there is a condenser. Condenser, and it is rejecting the output, is then throttled. This is our throttling device, or we can also call it expansion valve. Okay, now it is connected to our evaporator. Connected. Evaporator. Okay, now this condenser is further connected to our generator. So this is our or I can this is our generator. Okay, and here it is this generator is having some liquid phase and some in vapor phase. Okay, here is the absorber. It is absorber. Okay, or let's write absorber here. Absorber. Okay, now this is pumped. Okay, so first let's show it here. The evaporator exit is in absorber, and the liquid from absorber is pumped into generator. Okay, now this liquid is pumped into generator. This is a pump. Okay, now from here weak solution is throttled to absorber pressure. This is our press reducing valve. Okay, now one more thing, that there is also some, let me draw it whole. Okay, Okay. Now this evaporator, this condenser is cooled using, let's say, cooling water. Okay. Cooling water in and out. Okay. Similarly, in case of evaporator also, there is a cooling coil attached here. Okay. Now in generator also there is a cooling coil, or we can our basic purpose is to heat our generator. Okay. So let's discuss what are the, steps, what is the process that follows in our VRS cycle. Okay. Now let's talk about how does the cycle work. Okay, so let's consider water ammonia, as I have discussed that uh, different types of combinations. Okay, so water ammonia, let's consider ammonia NH3 plus water plus H2O solution. This is our refrigerant here. Sorry, ammonia is our absorber or absorber, or water is our refrigerant. Okay. So what happens that weak solution of here in evapor, since water here, sorry, ammonia is refrigerant and water is absorber. Refrigerant and water is absorber. Okay. Since ammonia is our refrigerant, so what happens that ammonia here in evaporator, enters from here, enters the liquid ammonia and H2O. Okay. And in the evaporator, after the evaporator, what happens that it receives heat, and after receiving heat it transforms into vapor form. Okay. So since our NH3 is refrigerant here, so let's say that at the exit of evaporator we have ammonia vapor. Okay. Now what happens in absorber? In absorber, when ammonia vapor enters, here. Okay. This is our NH3 vapor. Okay. What happens in case of an ammonia vapor when it enters the, and here, since this is our absorber, this is our H2O. So when it enters the water, so it is soluble at this low pressure of evaporator. This is soluble. Okay. Now what we do, as the here temperature is also low of water, as the ammonia vapor is exiting from the evaporator, the water in the absorber is simply absorbing it. Okay. And while absorbing, the heat of the ammonia vapor is retained by water. Okay. And hence the water temperature increases. Now what happens that in case of water temperature increases, the solubility of ammonia decreases. Okay. But one more thing happens, that is when this ammonia vapor will be absorbed by our water, so pressure inside the absorber will be decreased. Okay. So let me redraw this line here. So this should enter. Okay, let me show it like this. Okay. So when ammonia vaporized, ammonia vapor is absorbed by the water absorber, that is in liquid form. So in this case, our pressure in this region will be reduced. Okay. And since pressure in this region is reduced, so it will suck more refrigerant ammonia vapor. Okay. And it will absorb, water will absorb more amount of ammonia. Okay. And thus the temperature of water keeps on increasing. Okay. And as the temperature of water increases, the solubility of ammonia vapor will be decreasing. So we have to cool down our absorber. Okay. So we are circulating cooling water into absorber to cool down our system. Okay. Now since the system temperature decreases, so solubility again increases, and the same cycle is maintained here. Okay, now let me now what happens that since now this water is a strong solution of ammonia, so this water is pumped, like this strong solution of ammonia is pumped to our generator. Okay, and in generator what is happening, there is a there is heating now this heating can be done by solar heating, or can be done by using steam or gas burner or heating oil, anything. Okay, so we are supplying heat to the generator. Okay, huge amount of heat to generator. Okay, now since we are supplying heat, then this strong solution of NH3 plus, this is NH3 plus water. Now this strong solution, what will happen here ammonia vapor will be released from this point. Okay, ammonia vapor, NH3 vapor is released. Okay, at high temperature ammonia solubility in water will be less, and hence the ammonia vapor will be released. Okay, now this high pressure ammonia vapor, high pressure ammonia vapor is sent to condenser, where it is cooled, and after the pressure, reducing its pressure, we sent it again into evaporator. Okay, and this cycle continues. And what next what happens here in the case of generator, since on heating and our ammonia vapor is released from water, so the weak solution of ammonia that is remained in the generator is what it is sent back to our absorber by reducing its pressure. Okay, and this case this cycle continues. Okay, so there are two cycles here. One cycle is between analyzer, pump, generator, and pressure reducing valve back to absorber. The second cycle is this whole cycle. Okay, I hope you understood till here. Now if you notice one thing here, what happens that when, like here I have told you that ammonia is absorbed in the water, and this water is this strong solution of ammonia is like pumped to generator. Okay, in generator it is due to supply of heat, it is converted to an ammonia vapor. Okay, now this happens in an our ideal case system. Okay, now in real system what will happen in practical system, here will be NH3 plus water vapors. Okay, water vapor. Now this due to the presence of water vapor, now this complete ammonia plus vapor plus water vapor will be sent to condenser, and it is further reduced, and here we will get ammonia plus water liquid. Okay, small amount, although water will be in small amount, it will be present here. Okay, and when after this is moved to evaporator, after evaporator here we will ammonia vapor plus water vapor. Okay, and this is again will be sent to here, and this cycle will continue. But what is happening here, this water, when it will go to through all the system, so there will be corrosion, and it will affect the system negatively. Okay, now what we have to do, we have to retain as much water as possible in our absorber only. Okay, we don't want to pass the water through a condenser, expansion valve, and evaporator. Okay, in expansion valve there will be too much of our corrosion. Okay, it might be blocked due to presence of water molecules. Okay, so what in that case what we do, we install some more components. Okay, now let me mention them here. Now this here we have talked about simple VARS. Okay, VARS. Now if we talk about the practical vapor absorption system, there are some additional components. In case of practical, what we do between the our outlet of your condenser and outlet of evaporator, we install a heat exchanger. Okay, so let me install a heat exchanger here. Okay, and similarly here we will also install a okay. Now what happens here, we have installed a heat exchanger. Okay, so this is our heat exchanger. So what will it does, it will increase our temperature of outlet of evaporator, and here the presence of ammonia vapor present will be heated further. Okay, and now this will be supplied to our absorber. Okay, now let's say there is our absorber. Or let me move it downward a little bit downward. This is our okay. Let's say that it enters the heat exchanger, and after that enters the throttling valve. After entering evaporator, exchanges heat with our condenser output, and then it enter the absorber. Okay, now of course we know that in this absorber there is our absorber. Okay, that is our water. Okay, now in this case we also know that in here cooling coil is maintained. Okay, cooling water is circulated. So this system is our practical vapor absorption system. Okay, here what happens that let me tell you in detail here steps. So after exiting from the evaporator, it is ammonia vapor, NH3 vapor, and it is further heated in heat exchanger, and after that it is sent to your absorber, where absorber it is H2O, but in here there are NH3 plus H2O vapors. Okay, and here will be also NH3 vapor, and this will create the solution, increase the solution, the amount of ammonia in solution. Okay, and so the pump will pump a strong solution to our after exchanging heat from here, it will be sent to analyzer, and I will tell you what is analyzer and generator. I have already mentioned you. And in generator, what happens that after entering the entering our analyzer, it enters back to your generator. Okay, and here since we know that at this point you have high pressure due to after pumping, and you have supplied the heat QG to generator. So at higher temperature your ammonia vapor will be formed, and these vapors will move upward from ammonia, and water vapors will uh, move in analyzer. Analyzer is basically consists of your parallel plates, so it is used to increase the surface area contact of the vapor. And in this what happens that here, as I mentioned you previously, that there are okay, wait, okay, so there may be like in generator, after generator there might be your ammonia and water vapor present at the exit of generator. So to remove the water vapors, we have installed analyzer, and most of the water vapors are left behind in the generator, like condenses on these surface plates. Okay, surface of these plates, most of the water vapor is condensed, and only ammonia vapor is like exiting from this analyzer. Okay, and what happens that after exchanging after like convert into an ammonia vapor, the remaining weak solution is sent back to weak solution is sent back to our heat exchanger, and after it we have performed pressure reduction. We pass through it through pressure reducing valve, and we sent it back to our absorber. Okay, and what next happened that let's say that there might be some additional water vapors left at the exit of your analyzer, and this will be removed by with the help of your rectifier is also known as dehumidifier, and the like the water which will be condensed here will be sent back to your analyzer. Okay, and now here we have only pure NS3 in vapor form. Okay, now it will be condensed here to our NS3 liquid, and that is will also be pure. Okay, and after like exchanging heat, its temperature will be reduced, and it will be expanded to evaporator, and here again it should be NS3 liquid, and after it will be NS3 vapor again. Okay, so this cycle continues. Okay, I hope you understood the practical vapor absorption system. Okay, sorry, one thing correction here, this is not dehumidifier, this is dehydrator. Okay, so this you rectifier is also known as dehydrator. Okay, now you might be thinking why this heat exchanger is installed here. Okay, so this weak solution which we have extracting from generator is at very high temperature. Okay, but in our absorber we are like using cooling water to reduce the temperature. Okay, temperature of the fluid, so that it can absorb more amount of ammonia. Okay, but here what happens that in generator we are supplying heat, so this like the fluid which you have sent through pump need more heat. Okay, and this the the fluid that is weak solution need to be reduced its temperature so that it can reach to this temperature, and of course the pressure with the help of pressure reducing valve. Okay, now we can utilize this heat here in case of our pump output, and when we will send it here, so we will get that we have our this strong solution will have high temperature. Okay, and this weak solution when it reaches here, so we will get low temperature. Okay, so both of our problems and both things are like satisfied. So we use this heat exchanger here. Okay, and one most important point I should mention it here only, this vapor absorption system is used on very large scale operations. Okay, now let's calculate the COP of your vapor absorption refrigeration system. COP of vapor absorption refrigeration system. Okay, so to calculate the COP, we have to first see how the heat interaction is taking place and how is the work interaction is taking place in your system. Okay, so let's say that this is our absorption system which we have installed. Now this absorption system is interacting with your evaporator. The absorption system is interacting with the evaporator at temperature TL. Okay, and it's providing the heat QL to your system. Okay, the ammonia vapor which is entering the absorber has heat QL. Okay, and this absorption system is further interacting with the pump. Okay, here pump is installed, and this pump is supplied with the work W, which can be like, okay, so let's say work done by pump, work P. Okay, now there is also a generator. This absorption system is also connected to a generator. Generator at TG. Okay, TG. Okay, and it is supplying heat QG to your absorber. Okay, so from here you can see that this is a absorber, this is your observer. Okay, it is interacting with your generator, interacting with generator with your evaporator. Okay, and is also interacting with your pump. Okay, and this in turns, like after absorbing all this, it supplies this heat QC at condenser to condenser at TC. Okay, I hope you understood this point. Okay, now if we want to calculate your COP, so we can say that by like first like conservation of energy, we can say that QC is equal to, or we can like apply first law of thermodynamics. We can say QC is equal to QG plus QL plus WP. Okay, this will be our first law of thermodynamics. Okay, now from here what we can do, we can like we say that work done by pump is very less respect to with respect to QG or QL. Okay, so we can write QC is equal to QG plus QL. Okay, so this is our equation for heat transfer to condenser. Okay, now now from we can say that if the system is like if we apply the system to be like, say, perfectly reversible system, if we say that system is perfectly reversible, and which system is perfectly reversible? Absorption system is perfectly reversible. In that case, what will happen? Our delta S will be, or we can say that according to the closest inequality, del Q by T is equal to 0. So from here we can write QG by TG plus QL by TL minus QC by TC equal to 0. Okay, since we have already neglected your pump work, so we get this equation. From here we can write QC by TC is equal to QG by plus QG by TG plus QL by TL. Okay, and this QC like further we can substitute this value of QC here. Okay, we will get after substituting the value of QC, we will get QG plus QL upon TC is equal to QG by TG plus QL by TL. Okay, and why we have done this? So if we see that there are three here like temperature terms here, TG, TL and TC. Okay, this temperature we can measure easily. Okay, generator temperature we can measure, load evaporator temperature we can measure, condenser temperature we can measure. Okay, if we talk about heat, then Q generated, we have supplied it, we can measure how much heat we have supplied it. Okay, Q load, this is what we get. Okay, this is our effect. We can also calculate what is the Q add. If we talk about QC, it is directly reached to the atmosphere. Okay, so this term is like what we can do here. So since this term is difficult to determine, we can likely substitute in terms of QG and QL. Okay, So if we substitute this in form of Qg and QL, we get this equation. From here we can write, like if we let's say, okay, one more thing here. If we want to write COP will be desired effect. Desired effect is our QL. I think you know this. Desired effect is QL. Let me write desired effect upon input. Desired effect is QL. Input is our QG plus WP. Now if we say that WP is negligible, then we can write it as QL upon QG. Okay, so from this relation we have to find QL and QG values, or QL upon QG values, such that we can find the rest of the values. Okay, so we can write QG times of 1 by TC minus 1 by TG is equal to QL times of 1 by TL minus 1 by TC. Okay, so this equation here, from here we can write QG is equal to QL times of TC minus TL by TL into TG upon TG minus TC. Okay, so from here we can write our COP value, or COP maximum. If we talk about COP maximum value, can be written as QL by QG. And why it is mentioned COP maximum? Because work done by pump is neglected. Okay, if this work is considered, then this won't be maximum value. Okay, and this can be written in form of TL upon TC minus TL into TG minus TC upon TG. Okay, now from here we can say that this expression here, TL upon TC minus TL, is in form of our COP of Carnot and this is it can be done like mentioned as COP of efficiency of Carnot efficiency. Okay, so we can write COP max for what? For our VARS can be written as COP Carnot and into eta Carnot. Okay, now the shortcut, if you want to like calculate the value of COP for VARS, at what temperature, between what temperature we should consider Carnot, and at what temperature we should consider your COP. Okay, so since there are three temperatures, TL, TC and TG, we will represent first all three of them. So TG is the highest, we will keep it at top. So this is our TG, or let me write it like this. There is TG. Okay, then after that TG, after that we will get T condenser. Okay, then we will get T evaporator, T lower. Okay, so between lower two we have to like here we have to install our refrigeration cycle, of course, refrigeration, and here we have to apply our engine or heat engine. Okay, so from here we will get our eta Carnot, from here we will get our COP Carnot. Okay, and since we are talking about refrigeration, this COP should be in case of refrigeration. Okay, I hope you understood this point. Okay, with this we have completed our topic, that is COP of your VARS system. Okay, so our next topic is domestic Electrolux or Electrolux refrigerator. This Electrolux refrigerator works on three fluid system, principle of three fluid system. Okay, there is no solution circulation pump. Like in case of your vapor absorption refrigeration system, we are using a small pump to pump the water from lower pressure to higher pressure. But in the case of Electrolux, there is no need of pump. Okay, we will only supply heat. With the help of heat only, we will raise the temperature, raise the pressure of the liquid from condenser pressure, from the evaporator pressure to condenser pressure. Okay. Now this third fluid, like this is three fluid, so similar to VRS, the two fluids will act as one as a refrigerant, another as will act as our absorber. The third fluid which will add in this will act as will what will the third fluid do? So it will generally remain in the evaporator, okay, and it will reduce the partial pressure of refrigerant such that it will evaporate at a low pressure and at a low temperature. Okay, so if we talk about ammonia plus water plus hydrogen, so here we can say that ammonia is our refrigerant, this is our water is our absorber, and this hydrogen gas will act as our pressure regulator, as our pressure regulator. Okay, now here are some important points regarding this. So our like we know that NS3 is refrigerant, H2 is absorber. These two will act same as they were acting in the VRS cycle. Okay, now this H2, if we talk about hydrogen gas, if we talk about hydrogen, it only travels between circulates from absorber to evaporator, and back. So this hydrogen gas only moves from absorber to the evaporator and back to the absorber, and this helps to raise our. Now what happens in this, let's say that our ammonia vapor after the condenser is is flowing to our, so it happens that the whole process in the Electrolux happens under the influence of gravity. Okay, so under the influence of gravity, our refrigerant at the exit of your at the exit of your condenser, let me draw a diagram first. So let's say that let me draw it here. Okay, so let's say that this is our condenser, and of course there is cooling water inlet and outlet, and this condenser the refrigerant, that is NS3 refrigerant, will be moving under the gravity into your evaporator. Okay, evaporator. Okay, and in the evaporator, along with if we talk about evaporator, let's say right here evaporator, so along with ammonia, that is our NS3, our hydrogen gas also be present. Okay, so due to the presence of hydrogen gas, our partial pressure of ammonia will be reduced. Okay, so since the pressure is reduced, it is acting like in same way as if we have applied a throttling valve here. Okay, but we instead of installing a throttling valve, we have reduced the partial pressure inside the evaporator only. Okay, now it is moved to our absorber. So this is our absorber, and this hydrogen gas also present here, hydrogen gas plus ammonia plus water, all of threes are present here. Okay, and this is our water. Sorry, this water will here absorb an ammonia, and hydrogen gas will only hydrogen will remain here. Okay, this ammonia will be absorbed by water, and only hydrogen gas will remain here. Of course, there will be the circulation of cooling water here, and this hydrogen will like move between evaporator and our absorber. Okay. Now this ammonia liquid from here will be sent directly to, I mean, ammonia plus water will send directly to our generator, and this will also occur under effect of gravity. Okay. And after heating we will like send it to, let's say, our separator or analyzer, and after that again to a condenser. Okay. So this cycles continues, and of course there is analyzer too, we will also move to absorber and to and fro motion. Okay. So I hope you understood this Electrolux refrigeration, and this is only possible for a very small scale, very small scale operations. Okay. This is generally used in our domestic refrigeration in early times, not nowadays. Okay. I hope you understood this point. So with this we have completed our chapter Vapor Absorption Refrigeration System. Okay. And in next lecture I will be discussing the question related to this chapter only. Okay. So thank you for today.